So, hello everyone, and welcome to the ninth event in our special online meetup series hosted by the Web3 Developers Underground. So, before we'll dive in, let me briefly introduce our community and say hi to Tsahee here. Great to have you. Um, so, about the Web3 Devs Underground, we are a community of Web3 developers and builders founded on the open source values by Shaoli Redwan and Roy Osherov. Since our inception 3 years ago, we've consistently hosted in-person events, bringing together some of the brightest technical minds in the space. Recently, we have expanded to online meetups, and we're committed to delivering top-tier technical content to the global Web3 community. We're thrilled to have all of you with us today. So, to stay in the loop for future events and updates, please make sure to join us on all platforms: X, Luma, Meetup, YouTube, Telegram, and more. They're all available on our Linktree or website at web3devs.org. So, a special thanks to our community sponsor today, Masterkey VC, an early stage venture capital firms focused on infrastructure and deep tech across the Web3 ecosystem, with a team of 16 world class cryptographers and several technical experts, led by our managing partner, Shaoli Redwan. Masterkey operates across all major crypto hubs. So, now, without further ado, I'm honored to pass the mic to Tsahee Seidenberg, um, distinguished backend at Offchain Labs. So, Tsahee, the mic is yours.
Hi, thank you very much. I'm Tsahee Seidenberg. I am the tech lead in the what we now call the platform team in Offchain Labs. I develop Nitro, the Nitro node, and today we'll have a talk with two distinct parts. Um, the common theme will be WASM, but WASM will be used very differently. The first part, we're going to talk about how Arbitrum actually works, how Arbitrum works in very, very deep details. In a way, it's how other optimistic rollups work as well. But we've chosen WASM as the basic architecture. And we'll talk about what it means to prove Arbitrum and what it means to have an optimistic proof and what it is that we're proving. And everyone is talking about fraud proofs. So we'll show what a fraud proof can actually prove or not. In the second part, we'll talk about an Arbitrum specific technology, which is a stylus, which allows people to develop WASM smart contracts and have them on and execute them on Arbitrum. And we'll talk about how that works. Also, we'll go quite deep into how stuff works and a little less about how to use it, but that's available. Let's talk about let's talk about proving Arbitrum. How we actually prove on chain the state of the Arbitrum rollup, and we'll start with a toy example. And the toy example is this. Say I want to have this computation, right? I want the factorial of 1 billion, and I want the factorial of 1 billion modulo some large prime. On one hand, like it's pretty straightforward. If I want to know it, all I need to do is write some code, right? I'm a programmer. I write code in C. So this is generally what my code would look like. And I'll write C code, and then I will compile it, and then I will execute it. I think there is I'm going to do it a little deeper than that. Share screen window. I hope you can. Great. I hope that you can see it. I didn't want to bother too much with the input outputs, so I'm sorry about that. But generally, what I have here is a very, very simple C program, right? And it has the factorial modulo code. It's very simple. I'm not trying to be super optimal here. And what I do when I want to compile it is, first of all, I call a compiler, because nobody actually executes. The computer doesn't actually execute the C code. What it does is we call a compiler, and we compile our program. And when we compile it, it turns into an assembly. This here I'm running on a Mac, so it's an ARM processor. So if I look at the code that I executed, the code that I compiled, here we can see I didn't use any optimization, so it will be easier to see. But we can see the functions that are created, but they are basically transferred to something that's way more, that's much more basic, right? In the code, we have different variables that mean different things. Here, all we have is a very simple set of registers. The instructions here are branches and moves and multiply, and all are working. But this is a very, very simple set of instructions called an ISA, and this is specifically the ARM ISA. After I created something pressed. I'm in Hebrew. Okay. After I created a program, I can execute it. Now it's something that the computer can execute. It takes some time to execute because I asked it to do quite a hard computation, and so it takes a little while. But in the end, I get a result, and not only I get a result, anyone that will execute the same anyone that executes the same thing will get the same result. So we can all agree on what the result is. But agreeing on what the result is not enough, because the fact that you and I can agree still leaves an open question, which is, how do I prove on Ethereum? How do I prove on chain this result? Right? Because the fact that I know it and you know it doesn't mean that Ethereum smart contract knows the result. So the simplest way to do a computation, to prove a computation on Ethereum, is to execute it on chain. So if I want to execute it on chain, what I can do is I can write a smart contract. I can write it in Solidity. Solidity is already a little problematic. It already has some quirks. It's not the language that most programmers know how to write in, but it's okay. I can write a large. I can write this problem in Solidity, and then I compile it. Solidity is also compiled to EVM. EVM is the assembly of Ethereum. EVM is also quite. You also get very simple instructions like tag and dupe, and like it's also a very, very specific set of instructions, and that's called the EVM. And then I take this EVM, I deploy it to the smart contract. I can execute it on chain. Two problems here. The problem is executing on-chain is very expensive. If I do a lot of computation on-chain, it becomes hard for the computer. It takes lots and lots of gas. More than that, at some point, and I don't know exactly where the numbers are, I didn't check it, but at some point, it's very easy to define this problem in a way that it will be actually impossible to execute it on Ethereum, because it can take years or hundreds of years to run on Ethereum, even if you take up the entire block space. So executing on-chain is possible, but it is a limited resource. You cannot do everything there. And then what I need to do is I go to the next phase, which is on-chain proving. So what I want to do is not compute the entire thing on-chain, but I do want to prove on-chain the correct result. And the way to do it and let's talk about how we do it in the optimistic proving approach. So first thing I will do is I will compute locally. I will compute locally, and I will have that result, the same result that everyone else that computed that same problem will have. Then I will take my answer and I will submit it to Ethereum. I will go and tell Ethereum, hey Ethereum, I claim that 1 billion, the factorial of 1 billion modulo something. I have a result. This is my result, and I will add stake. I will not just say I claim this. I will also put some money behind this claim. I'm backing up this claim, and then I need to be able to prove to the smart contract that my result is actually correct. How do I do that? First option is the simple one. In the first option, I told the smart contract what I think the factorial of 1 billion is, and time passed. And nobody else said anything else, right? I said this is the factorial. Nobody else had a diverging opinion, so it becomes pretty easy. If there is only one option, the smart contract after a while assumes it is correct. What is a while? When you take that into account, you need to think about what type of attacks you want to be able to withstand. We want to make sure that if there is lots of money behind this claim, right, that I cannot say, this is the factorial, and then just just do a denial of service type thing where I do not let conflicting transactions go on Ethereum. Denial of service attacks on Ethereum are very expensive, and we have the current general agreement, which was started by Vitalik when he described the optimistic proving lots of time ago, is that waiting 1 week is enough. It's enough to not just withstand the specific attacks, it's enough to withstand large attacks on it. Even if someone does a large scale attack on Ethereum, then within a week, it should be enough time for the community to go and understand that there is an attack, solve the attack, and hard fork if needed. That's based on things that actually happened in history. So the simple way is that somebody said the right value. Nobody tried to say anything else. A week passed, and now the smart contract knows what's the modulo of 1 billion. But it is possible for someone to have a wrong assertion, right? It is possible. The smart contract cannot prevent. It doesn't know that I'm doing the right assertion. So what happened if I go and I claim something false. If I claim that that's 1 billion, that the factorial of 1 billion is something else. Well, now what will happen is a challenge, meaning somewhere within that week, somebody else that cares about the same state will come up and say, no, that's wrong. That's actually not the factorial of 1 billion. The real factorial of 1 billion is something else. And to prove that I'm correct, I'm not just giving you the factorial of 1 billion, I'm also giving you the factorial of 500 million. So I'm saying, this is my assertion, right? This is the large thing that's happening. And I make a further, more specific claim that supports my claim. And that's the factorial of 500 million. After I've done that, I'm now considered the winner. So if now a week passes and nobody and the first party doesn't answer, I win. However, if he does answer, what he will do is they have two options. The first option is to say, no, you're wrong. What that party said about the factorial of 500 million is entirely wrong. The real factorial of 500 million is something else. And further than that, the real factorial of 250 million is that. The other option they have is to say, well, what they said about 500 million is entirely correct. However, that doesn't lead to the decision of to their claim of factorial of 1 billion. It leads to mine, right? So I can say, yeah, this is, so the factorial of 500 million we agree on. We still don't agree on the factorial of 1 billion, and I'm giving another point in the middle, the factorial of 750 million. But in any way, what we're doing is we're always narrowing what we didn't agree on, right? So if at first we didn't agree on the factorial of 1 billion, now after my step, we don't agree on we don't agree on 500 million steps. It can either be the first 500 million steps or the second 500 million steps, but that's what we don't agree on. After that, the second actor will narrow it down further. Does it agree with my new assertion, and where lies the disagreement? So in every step, we cut the disagreement in a logarithmic way. So we cut the disagreement by a lot on every step, and we make it smaller and smaller and smaller until theoretically we have to get to a disagreement on one step. So at some point, we will say, we will both the challenge participants will agree absolutely on what's the factorial of this number, and disagree on what's the factorial of the next number. And at this point, we know that whoever has the correct assertion here, whoever has the correct implementation here, must be the correct party. They will be the winner of the challenge. How does the smart contract know which one of those two is correct? Well, this one is easy. Now we don't need to do a billion computations. We just need to do one. The factorial, if we both agree on what's the factorial of this number, the factorial of the next one is just take this, multiply it by the next number, modulo the modulo. This is a simple enough computation that can be done on Ethereum. And this is what we in Arbitrum we call the one-step proof. So it's proving the single step. And after the smart contract knows which one of us won the one-step proof, they are the ones that won the entire challenge. Now, this is a small introduction to Bold. Bold is a fascinating protocol that allows the one honest party to challenge, to fight many multiple challenges at once. It allows multiple honest parties to be on the same side trustlessly. So you know if someone did an honest move, any honest party knows about it and can take it further. So if one honest party stops in the middle, any other honest party can keep up from that point. It's a great, amazing protocol. We're not going to go into details about how it works more than we've covered by now, but the essence of it is we narrow down a large disagreement into a single step. We prove that single step on Ethereum, and that's how we choose the winner. So that was nice, right? We've shown how we can prove the factorial of 100 billion. And proving the factorial of 100 billion comes from the fact that a single step of computation is just modulus multiply. But we want to take it further. We want to take that approach and now be able to prove anything. Not any event, but any computation. So I want to be able to take any code. So I want to be able to take any piece of code and prove its result, not just something generic. And I want my proving system not to be very dependent on what is that thing that I am computing. So what I'm going to do now is I'm going to do generic provable computation, generic provable execution. So what I'm going to do is so how it works is I start by writing code. It can be, in our sense, it's mostly Go and some Rust, but the first example was C, so I'll stay here with it can be C. And I compile this code to WASM. WASM is WebAssembly. We will talk deeper about WASM and its properties later, but the basic idea but WASM is essentially also an assembly language, right? So there are there are a few known instructions that can be executed. And I take this WASM and I execute it on Arbitrator. Arbitrator is our machine. It's a machine that executes WASM. We'll talk more about it. But what it does is when I execute things on Arbitrator, this is what I can prove on chain. So I will execute it on Arbitrator. This will get me to a result, and this result can be proven on chain. So Arbitrator. Arbitrator is our WASM executor. It's written in Rust. It's a fully emulated machine. So it works just like any fully emulated. There are many fully emulated machines that like pretend to be another machine and execute that. It executes WASM. Now it's not exactly WASM, but it's close enough for our talk. And it's deterministic. So if you execute the same thing on Arbitrator 100 times, you will always get exactly the same result. It has hashable state, which we will talk more about soon. And it can produce one-step proofs. So first of all, Arbitrator is a virtual machine, and it's emulated and deterministic. If we look at what that means, Arbitrator in its essence is just like any other emulating machine. So it holds a virtual machine in its memory, right? So Arbitrator machine is divided into multiple modules. So every module is like a WASM binary that has code, it has its memory and global variables. The machine itself has a variable, has a stack, and has program counter which shows where it is in the current execution, and has something called the global state, which is its basic input output, and we will explain a little bit more about that later. But the arbitrator machine basically has in memory, it has a representation of a full machine, right? A full computer. This computer has a memory and it has a code that executes, and the arbitrator machine is like the processor, or the processor and the memory of this entire thing. If you look in how arbitrator machine works, it works like, again, any other fully emulated virtual machine, and in many ways like any processor. And how both virtual machines and processor work is they have basically, in essence, they have a large loop. And that large loop, what it does is it looks at the program counter. Program counter says what's the next instruction, right? The pointer to the next assembly instruction you need to execute. So we fetch the next assembly instruction, and we advance the program counter to the next assembly instruction. And then there is a large select, or a large, in Rust, these are called match. Right? So there is a large, so what we're doing is we're checking this instruction against every possible instruction that we support. So WASM has, for example, the instruction I32 EQZ, which is the WASM not. It is the current top of the stack 0 or not. So the execution of this instruction is we have the stack. We pop the first value in the stack. We check if this value is 0. If this value is 0, then we push 1 into the stack. If this value is 1, we push 0 into the stack. And that's how you execute this opcode, which is I32EQZ. We likewise have implementation for every other supported opcode. So this is how every virtual machine and every CPU essentially works. It's a large loop that goes and executes assembly instructions one by one. And the assembly instructions, as we've seen, are pretty simple, and there are few enough of those that you can implement all of them. So that's how. So that's also what's at the heart of the arbitrator machine. Another important property about this loop in arbitrator is, as I said, it's deterministic. It's deterministic, meaning if you will execute the same thing 1 million times, you will get the same results 1 million times. Machines non-determinism tends to come from a few places. The two most important ones are when you have multi-threading, and when you have any time dependency. So if you can check what's the current time, your machine is non-deterministic, because if you run it 1 million times, you will run it in 1 million different hours. If you can check how long it took you to execute something, it's not deterministic, because executing the same instructions will not always take the same amount of time, because sometimes other things are happening and other things are in the cache and other things are not. So there is no notion of time, and there isn't real multi-threading in Arbitrator. So everything it does will always yield the same result. Another interesting property of Arbitrator that isn't correct for most virtual machines is that it's hashable. And when I say hashable, I mean there is a single, I can take the entire state of the Arbitrator machine and condense it to a single hash that will be dependent on every bit of state that is anywhere in the Arbitrator machine. So every bit of code, every bit of memory, and everything in the stack all gets hashed together to what we call a machine hash. And this hashing is, as you would expect, it is structured, right? So what I do is basically I hash the code into one like Merkle-like structure, and I hash the memory in a separate hash, and I hash the global variables in a separate hash, and then I take all of those and I hash them into the module hash, and then I hash all the modules and get like the modules hash, and I build this hash from different units. This is in comments here. I put the actual source code. It's all the source code inside the Nitro base, if you want to take a look. But this is basically the source code where every bit of state in the Arbitrator machine is condensed into that single hash. And the last thing about the Arbitrator is that it's provable. It can produce one-step proofs. So if we agree that machine hash on step n is one thing, then I can absolutely prove what will be the machine hash in step n+1. And since that's correct, by the extension of bold, as we've seen, if I can prove a single instruction, that means that if I can prove if we both agree on the first machine hash, on the machine hash that was when execution began, then every step is provable, right? Because they're all just the next step after the first one. And when I say I can prove things on chain, I absolutely, of course, mean I can prove it on chain. And we will now dive into how I can prove arbitrator state on chain, how exactly that works. So when I say I am proving something on chain, what I'm doing is what I mean is I have a smart contract. I have a smart contract that accepts those proofs. That smart contract accepts has an entry. The entry is called prove one step, and it has two important inputs, which is the previous machine hash and the proof, which is like a large array of bytes, and this function will return what's the next machine hash, and bold will connect to this, and that's how it can prove always the next step from the current one. Okay, so how does one-step proof work? First, to describe it, we will say that we also have arbitrator machine in Solidity. So it's the same machine that we have an implementation for in Rust. It also has an implementation in Solidity. But the Solidity implementation is not a full, right? The Rust implementation, the one locally, will store all the memory and all the stack and all the code. In Solidity, we don't do that. That's going to be way too expensive. What we do have is we hold a struct that holds some bits. It holds some hashes from the entire state. So, for example, it holds the hash of all the modules. It holds the hash of the stack and the first few elements of it, and it holds the program counter, so the pointer. So we have a struct that holds some parts of the arbitrator machine, and the other parts, and the parts that it doesn't hold the full state of, it holds the hash of those things. So because I have the hash of the modules, I don't need the specifics, every bit of state of every module, because I know that hash of the entire modules. That means the arbitrator machine does have enough state to be able to compute a hash of it, right? So we can take hashes of the different elements that we have and concatenate them and catch-up them, and that will give us the machine hash, the same machine hash that is the same machine hash that was computed by the Rust code. So if I look at a one-step proof and check what it has. So the first part of the one-step proof will be just this, will be a serialization of the machine. It comes with, so it has like hashes of the modules, hash of the stack, some parts of the stack, the program counter. It has all of those. And the first thing I will do in one-step proof is I will deserialize machine. I will read the machine from that proof. And then I will go and check that the machine hash I got, and then I will hash that machine, and I will check that this machine hash really fits the before hash, the before hash that my one-step prover got. So I know I have now proven like every bit of state that is in the stylus presentation of the arbitrator machine is proven by this machine hash. I will later prove the module hash. So I also have, like, just like there is a representation of the machine, there is also a representation of a single module. And this representation of a single module is also condensed to enough to get a module hash. And I can check that, and the proof will have both data for the module, and with the data for the module, I can compute the hash of that module. And it will come with a Merkle proof that proves that this module really is one of the modules that I already know are correct because they fit the machine hash. So I have now proven that I know parts of the module, and I know that this is consistent with the machine hash that I got. The next part, just like we proved the arbitrator machine from the machine hash, and then the module from the arbitrator machine, now we can prove part of the code. So again, the module representation has enough to, and I know what's the interesting part of the code. I know what's the interesting part of the code because the program counter, which is also proven, the program counter, as we said, this is the pointer to what's the next instruction that will be executed. So the program counter is actually a pointer into the code that says, now I'm reading, like, the next instruction that will be executed is function module number 1, function 17, instruction 3. And now I can prove, thanks to, from the machine hash, thanks to the arbitrator machine, and thanks to the module hash, and thanks to the module, I can prove the code that is in that exact spot. So the next part in the proof will actually be the instruction that is going to be executed. So now I have the program counter, I have the top few elements of the stack, and I have the next code that's going to be executed. The next part in the one-step proof solidity is to just follow the same steps of what you do, of how do you execute an instruction. So in solidity, we know the current program counter. We will advance it by 1. We will advance to the next instruction. And then we enter in solidity something like the large select. So we know the next opcode, so we are just matching it against every possible opcode that we support. And uh, and then we will go to the implementation that fits this execution. So execute EQZ, we saw its implementation in Rust, in local execution. This is its implementation in this is its implementation in the Solidity. So its implementation in the Solidity will also go to the value stack, will pop the head of the value stack. The way it's stored is, I really like the way that the value stack is stored, but like it has the few top elements. It has the few top elements in our Solidity structure, so we can know what was the first element. We check if the contents was 0 or not, and according to that, we will push into the stack the 0 or not. So now the blue here shows. So the blue here shows the parts of the machine, of the Arbitrator machine in Solidity that we changed from the input, right? So we changed the program counter when we advanced it, and we changed the head of the stack because we popped one element and pushed one element. So we changed some elements. Now all we need to do is compute the hash of this new changed Arbitrator machine. So the basic sauce, the basic secret to how the Arbitrator machine is provable is that every single opcode only changes very, very small parts of the entire state. And all we need to do is be able to prove every possibility of changing one part of state by one specific opcode. And after we've implemented for all opcodes what it will change in the state, and we can compute the hash of that changed state, that's how we know what will be the next machine hash. So in Nitro, what we said is, given machine hash is something in step n, I can prove what will be the next machine hash in step n+1. Using both protocol, I can say that now, given the first machine hash, the entire execution is provable. And in the Arbitrator machine and in the code that we're using it with, what it means is that if we know block n, if we know what was some block, and we know the input to the next block, then now what's block n+1 is provable. Assertions in Arbitrum are one level above block. So an assertion will prove many, I think usually many hundreds of blocks. So we take another bold step on top of the execution, and now we say that given assertion n, we can always prove assertion n+1. Now, what I told you is everything here, the Nitro node executes, the Arbitrator can execute every code, right? So I want to talk about a little bit. So this was the Arbitrator machine. That's like the bare metal of what things run on top of. Let's talk a little bit about what is that code. What is the code that's running on top of Arbitrator? And this code is also available. It is Go code. I didn't add the execution. I didn't add code samples here because for this one I thought that this very pseudocode will be better, but it exists. You can go and check it out. What it does basically, the algorithm that it follows starts with getting the previous block hash, reading what was the last block hash. Right? The next step is I load the next transaction. I load what I need to do. and then I execute those transactions. Those transactions can have relevant state, right? If when I executing a transaction requires reading some part of the Ethereum state that was in the last block to be able to compute what will be and what's the transaction result. Some of those transactions will be stylus transactions. And after I executed all transactions, I now need to compute the next block hash and finish execution. So the first interesting thing. So most of the instructions here, and I'm talking like 99.999%, are entirely standard WASM instructions. But we do support some special operations for that connection to the rest of the world. So the first thing that we support is we said briefly that it exists. We said briefly that it exists, but is a thing called the global state. The global state has basically, for our purpose, the global state holds the block hash. So this is really the input-output mechanism of my this is really the input-output mechanism. So the first machine hash only depends on two things. It only depends on the global state, which is basically what was the last block hash, and the code. That's the only thing it really depends on. So this is how, and this is why the first machine hash is known to everyone that agreed on the last assertion, or that agreed on what was the last block. If we agree on the last block, that means we agree on what's the first machine hash. So the smart contract, the main.go will basically start with get global state. So it will read what was the last block hash. And after it computes the block hash, it will store it in the global state and then call halt. The halt instruction is also important because what it does is it basically sort of wipes the entire state clean. So the last machine hash also depends only on what's the next, only on the block hash. So if I say that that block hash is that the block hash in the end is something, then my claim is very clear as to what will be the machine hash that fits this block hash. So this is how we do so this is where the block hash comes into play. The next thing we do is we load the next transaction. So load next transactions deals with another special instruction, which is a read inbox. Read inbox can read the next batch that was posted to Ethereum. Arbitrum is a rollup, so we take all the transactions that you posted and post them to Ethereum. Read inbox is an instruction that can read those instructions back from Ethereum. The way it can read those instructions is that it's connected to the smart contract that we posted the transactions to. So this is also like a connection that the Arbitrator machine has to Ethereum, and that's where it loads the next. And this is the basic thing that from which we can prove what are the transactions loaded. The last interesting instruction is get pre-image. Get pre-image is an interesting instruction because we've said you can load. So to execute a transaction, you will have to load state from Ethereum, right? If the transaction is I want to send this many ETH to someone else, I need to check if that person even has that amount of ETH. I need to know what's the hash of the state and everything. How do we load all that state? We said we start with only the block hash. So we basically load everything with get preimage. Get preimage is an instruction that gets 32 bytes hash of a preimage and returns the hash that, like, the thing that hashed to those 32 bytes. And because of Ethereum, the way that Ethereum works, so in Ethereum, if you know the block hash, you can prove from it using get preimage. This is basically how you read the block header from a block hash. And in the block header, you will see the state root. And the state root is the root of a Merkle trie. And every bit of state in Ethereum is provable by just going with get preimage. Starting from the state root, you can get to each and every bit of state in Ethereum. So that's how we can read the relevant state. I said last earlier, but it wasn't the last step. The next step I want to talk about is a step that we added more than a year after Nitro was released, and most of what I talked about already existed in one way or another. We had a great engineer, Rachel. She said, well, if we're already working on Stylus, and we're already working on WASM, let's let our users also post WASM code directly. And the basic magic that makes it work, that makes everything provable, because for us, the most important thing is everything must be provable, is the link module special instruction. The link module special instruction, what it does is it can dynamically add new modules to the arbitrator machine. So this is an instruction that sits at the very base of why we can take WASM code that was sent by our users, not by us, and that was sent by users on chain, and we can take that code and we basically convert it into an arbitrator module, and then we can dynamically load this module, and we can jump to this module, and we can execute it. And that sits at the very base of the stylus, which I will talk about in a few moments. So thank you. This was the first part, how we prove Arbitrum. As the slides say, we are hiring. I'm going to take a few minutes to, I don't know, drink some water, or if anyone has questions, feel free to post them. And then we will talk quite deeply about Stylus and how it works and how people can use it.
Awesome. Thank you, Tsahee. We'll take a few minutes. Let's meet in 5. And by the way, guys, if any of you has any questions, you can feel free to send them in the chat in the meantime. We'll make sure to ask Tsahee once we're back. In the meantime, if any of you wants to scan the QR code, it leads to our link tree, which has all of our links, events, and everything else related to it. Hey Tsahee, we're back.
Hello. Um, yeah. So now we're going to shift gears or aspects or something, and we'll talk about stylus. Stylus is very yeah. What is stylus? So stylus is in essence, it's a way for users to execute WASM. So you can submit smart contracts that are working in WASM instead of Solidity. So instead of EVM. So why is that good? The most important thing about WASM is that executing WASM is very, very fast. EVM was never designed to be very fast. It has in basics, its basic element is 256 bits. It's not something that any computer does very, very quickly. So it was never designed to be fast. It was designed to be many things, but that was not a real design goal there. WASM was designed to be fast. So the first thing you get is that you can do a lot more compute heavy. You can be way, way more compute heavy when you are writing with WASM than when you are writing with Solidity. We have changed how the local memory is accessed, and but essentially, I think that WASM is the right tool to use. Stylus is the right tool to use when you want to do really complicated computations. And one thing that we've really made sure when we created Stylus is that it's fully composable with EVM. So it's fully composable with EVM, meaning that it can act just like EVM, and you can do anything that you can do with an EVM, including calling smart contracts. So you can have smart contracts written in EVM interacting with, so you can have an ERC20 that's designed in Stylus, and it can be exchanged by by an AMM that was written in Solidity, and the AMM will never know that it's interacting with something that's not a simple EVM smart contract. You can also have it the other way around. You can also have an AMM designed or any financial instrument designed with in a stylus interact with ERC20 EVM machines, for example. You can do any call. You can even do delegate calls to EVM. It's very, very designed to be very well integrated with how EVM works. And one thing that we so the two things that we believe make a stylus important is, first of all, really you allow much more compute to the user, and other than that, you allow users to write in let's say normal languages. Rust, you can write in Rust, in C, in assembly script, in Zig. Go does compile to WASM, but it has a huge runtime, so it won't work. But you need things with a very small runtime to be able to do it. But it's basically, you can open up to way more, let's say, mainstream development and developers. Before we go into stylus, and I want to explain why WebAssembly and what's important about WebAssembly. So we said that WebAssembly is essentially an assembly language, right? It has very simple instructions that are supported. It was announced about 10 years ago. In 2015, it took like 2 more years for the first, I think, candidate to be released. And unlike most ISAs, WebAssembly was not designed to be executed by hardware. Most ISAs are ARM, x86, RISC. They are all designed to be executed by hardware, by physical chips. WebAssembly was not designed for it. It was designed to be executed by browsers. So that's why it's called WebAssembly. It's like super fast JavaScript. It is used today in your browsers, in many websites, to do a lot of computation. But the basic idea behind the WebAssembly was that you can get much faster than JavaScript. Basically, the initial WebAssembly is also a lot about how it interfaces with JavaScript. In its base, WebAssembly is a stack-based machine. It has interesting safety checks, and it's a lot about security. So because it's designed to be executed by browsers surfing to websites, websites are inherently not supported. Not trusted. You inherently don't want to allow a website. You want to be very careful when you allow website to execute code on your machine. And sometimes you will get in a single website many instructions from many pieces of code from many different places, and you want to make sure it's very, very well protected, and that it doesn't have any option to run on your machine or do anything else. Today, it has very, very wide compiler support. Rust compiles to WebAssembly, WASM script, C, C++, LLVM. We have Zig, and Brainfuck even has a way to work with WebAssembly. It's a very well supported language and used quite a lot. So going a little bit deeper into that. When I say WebAssembly is stack-based, I mean that most instructions inherently interact with the stack. So EQZ, as we've discussed about it, as we've talked about it, it's an instruction that pops an element from the stack, checks it, pushes an element from the stack. const. The const instruction is an instruction that pushes an element to the struct. Pull takes two elements from the stack, multiplies them, and pushes an element to the stack. So it's using a stack basically for its computation and not registers. It's not a clean stack environment. It does have locals and global variables that are more register-like. So you do have like local get and the global get that will basically, if you want to do a computation, then local get will basically copy a local variable to the stack. A very important property of WASM is that branches and jumps are all structured. So in a usual assembly, what you have is a branch instruction that branches to some address or some offset. We'll basically say, take the pointer of what's the next instruction and move it to this address or move it by this much. WebAssembly does not have this. There is no way to jump to a random place. All jumps are structured. So you have an if, else, and and these are really like in a normal in normal assembly, in most machine assemblies, an if, else, and will be eventually compiled to conditional jumps, and they will all be like test this and then jump to this offset or to this address. Here there is no jump to address. There is no jump to offset. It's an if, else, and that are part of the assembly. More than that, even function calls. Function calls are not, again, in normal assembly, the call will basically be go to this address, there is a function there. But you can jump anywhere. A call in WebAssembly is a call to a function. Call 0, here it's 0 because there wasn't linking done, but call 0 is call to function number 0. There isn't any way to call something that's not a function. So you can only branch to a thing that's actually that you can branch to. Like there are also loops, and everything is inside the assembly. It's not just a C construct. Another interesting thing that WASM validates is it really validates the stack. So if you see that this is a function that has one parameter and one result, the linker itself makes sure that, and the compiler itself, they make sure that when you call this function, you have an I64 sitting at the top of the stack that's going to be a parameter. And it knows that when you return from this function, you will have a result that's a single I64. Everything, the way it interacts with the stack is very validated, right? So here you see a local get 0 that will add one element to the stack, and then local get 0 will read this parameter here, and EQZ will pop and push, and everything how it affects the stack is validated. And if you try to do if I tried to write that I64 EQZ before the local get 0, the compiler, the linker, will tell me this is invalid assembly. I cannot work with it before trying to execute before anything. It's even like here I have an if. The compiler will make sure you see that this if specified that the result is an I64. So we will make sure that every branch of that if interacts with interacts the same with the stack. So this will just push one to the stack, and this will add 2 elements. This is actually add 3 elements. Then there is a sub which will take 2 elements and push 1, right? It will subtract 1 from the other. So after those, I will have 2 elements in the stack. Then I call 0. I call actually the same function. So it will take 1 and push 1. So it doesn't change. And then multiply will take 2 elements and multiply them. So in the end of this, I also have 1 element in the stack. Everything is validated by design, by the assembly. You never execute, you never have to worry about, you never have to think about what happens if there isn't this element in the stack. It's always there because if it's valid assembly, if it's valid WASM. A small exercise. What does this function do? I'll go over it in a bit. So local get 0 will get the parameter. Parameter becomes like the first. So I get the parameter EQZ. Does it check if it's equal to 0? If it is equal to 0, I will just push 1 to the stack, and that will be the result. If it's not equal to 0, I will take this twice. I will add 1, I will like push 1 and subtract. So now I have in the stack the element and the element minus 1. I call 0, I call the same function. I call myself with the number reduced by 1, and then I multiply the result with the first item I put. What did I get? I got a factorial, right? This is a recursive implementation of factorial. This is a great example. I feel it in my bones. I must always say when I present those examples, never actually implement factorials as a recursive function. But it's a great and a simple example, so I use it here. I want to, before the CSDK, I will talk a little bit more about how to use Stylus smart contract. And the first thing you do is write WASM. You usually don't write the actual WASM. You write some other language and compile it to WASM. Then you take this WASM and you deploy it to a smart contract. When you deploy to a smart contract, it's not tested and not executable. If you just deploy, if you just send this, nothing, like it's basically sitting in a smart contract with a bunch of bytes that nobody treats. You later need to do a phase that we call activate. Stylus activation is something you pay for it in separate. You pay for it separately. And it does a few things. Activation, first of all, checks that the WASM you posted is valid, and it doesn't check only that it's valid. Also, a bunch of things that we put a bunch of restrictions to make sure that you're doing something that makes sense and that really works with the SDK, and you're not trying to import functions that don't exist, etc., etc. We do. Part of Stylus actually injects some code into your WASM, actually changes the WASM that you posted. You don't have to know it. I'm telling you it, but yeah, you can use WASM without understanding that part. And then it will compile to local machines. So when you activate, the smart contract, every node will actually take the WASM you posted, will do all those modifications, and will compile them to themselves. So if I have a node running on x86, it will compile it to x86. If I have a node running on ARM, it will compile it to ARM. And then the nodes have a compiled copy of your program, which is why they can execute it so quickly. And this is why we can actually allow you much more compute. And this is why we can charge very little gas relatively for compute in Stylus. The code modifications we add, the animation was added now, but basically we add some bits of code here into the WASM that charge gas. This is weird. This was weird to me when I first saw it, because like you're trusting the code to charge gas for its own. Like, why would you trust a smart contract to have code that does it? And the reason is you don't really you trust that the smart contract gave you valid WASM. As long as you gave you valid WASM, you can modify this WASM in ways that you know that in ways, and you know that because the WASM was valid, it can't touch anything that you do, right? We basically add new global new global variable that counts gas, and we in the start of every basic block we add code that modifies it. And another interesting thing is, because WASM is structured and we don't ever jump to offsets, we can add as much code as we want here, and it will still work the same, right? We can add code here, we can add code here, we can add code, but because branches were not branched to offset, it was branched to that place. That place never changed. Function number 0 is still function number 0. That if else are still as connected as they were before. So we can do lots of modifications on the actual code before we compile it, and we use this property. So now let's talk about how nobody, and I do mean nobody, actually writes stylus smart contracts. I will later show you how people do write stylus smart contracts. And we've created multiple SDKs. This and then share screen window. Yes. Share. We've created multiple SDKs. Can I do this? Yes. We've created multiple SDKs. The most widely used one is Rust. We will talk about, we will show examples and talk about Rust, but we also have a very, very basic C SDK. Nobody uses it. Why do I show it to you? I show it to you because, well, I like it, and because it's very, very low level. This is, instead, if I tried to show you how things work deep in Rust SDK, I'd be lost very quickly, because Rust is, because there are many layers of abstractions there. The C is a very, very bare bones SDK. This is why nobody uses it. But it's fun to look at. So this example is an ERC20 like structure, and this example mostly shows how it works when I say that stylus and the EVM can interact with one another. So if I created an ERC20, I'm starting with a Solidity implementation. Solidity implementation mostly to show you like the normal thing, right? The Solidity implementation will have something like total supply and an array of minters, and there is a mapping of from address to int that like marks all minters, and have a balance for from address to like to their balance. That's at the base of every like ERC contract. It's something like that. There are functions that you can call. Some of them are virtual and even pure that return function name or the name and the symbol or decimals of my contract. And you will have functions like mint that accepts an account and the value of how much to mint, and will only work for and should only work for minters. So I want to implement all of that in WASM, right? I want to implement it in somewhere else. And the first thing I'm going to show you, not this. Yeah. So the first thing, and this is an auto-generated. This function you gladly, even in this bare bones implementation, you don't have to write. But the first thing you need to do is to understand how people are used to work with EVM. And the first function you need to write is an entry function. So the entry function gets the input, and what it does is it reads the first 4 bytes of the input, compares them against different functions, and will call the correct function. Why do I need this? Well, this is transparent to most people who write Solidity, but this code actually exists in EVM in almost every Solidity piece you write. So if you write a smart contract which has multiple entries, what will actually happen when you try to call one of those functions is you will the environment, the JavaScript, the whatever, will create a function selector, which is created from its name and the type, will take those into 4 bytes, and that will be the start of the input that is sent to the ERC smart contract. So the ERC20 entry is simply a C implementation of that thing that in Solidity is usually implemented by EVM and is usually hidden from you, and you almost never have to worry about. But so this is the first thing, right? You understand what function you even need to call, and then you call the function. And if I look at Mint here, let's go to Mint. Minter and Mint. Okay, so Mint is a function that gets 2 parameters, right? One is the address, one is the uint 256. What was actually sent to the EVM are 4 bytes of the selector that says Mint, and then 32 bytes with the address, that the first few were 0, and 32 bytes with the input, with the amount that we want to mint. So the mint function will basically get storage is like a, never mind that, but it will be null, but that doesn't matter here. But what we will get here is the input, which will be those 64 bytes, and the length of the input. So the mint implementation, first of all, needs to check that we did get here from a minter. How do we check that we are from a minter? We check that we are from a minter using essentially a VM hook. So doing computation in WASM is easy, right? But every interaction you need to have with the EVM, if it's check who sent the message, or check the message value, anything that you can check in EVM, we need to translate or to read the arguments that you got, or write results, or anything that you can do, call a separate function, like call a separate smart contract, anything that you can do in EVM, we have to translate to a specific hook. So we created a function called, for this example, message sender. You give message sender a buffer, and what it will do is it will fill the address of the message sender into that buffer that you gave it. And that's how, in essence, Stylus will do anything that actually interacts with the EVM must happen in this way, must happen through functions that we exported. And another interesting point here is understanding where we need to store memory. So we have the address where we store what's some recipients, what's someone's balance, right? We need to store it somewhere. The EVM, for every smart contract, again, Solidity gives you maps and gives you arrays and gives you some very convenient functions, but the EVM doesn't have those. All the EVM sees is 32-byte key and 32-byte value. For everything you load and store to storage in Solidity, it ends as an EVM that reads or writes 32-byte keys to 32-byte values to and from 32-byte keys. So we do all of that here in explicit C code. So so for example, we need to do we need to check. So map slot, like, is you take the base of the map and you append to it the key that you are looking for, which will be the address of the contract that you want to know, and you then do catch-up of all of those, and then you know what's the slot you need to read and write the data from. So I like this implementation because it shows every bit of thing that you actually need to do to read and write, stuff from the chain. So if will that work? No. Wait. Okay, so this one I can leave. Okay. See, no, let's see examples ERC20. Is that clear, the text size? Great. So when you take a bunch of code, and so what we're doing here is we take this code and we create WASM. In the end, we get like an ERC20.wasm that we can look at. That we can look at the very basic of the assembly that we created. And one interesting thing to see here is you can, if you look at the WASM of your of a smart contract that you developed, you can see all the VM hooks that it used. Right? These are all the functions it will call, and our environment will knows those by name, and those names have an assigned type that they must have. Right, but you have a VM hook called storage load bytes, and that will load the key from storage, and message sender that we saw that will check who the message sender is. There are many more VM hooks than you see here. Those are just the ones that this smart contract used. And then what we do is and after I wrote my stylus, all I need to do is deploy it. So Cargo Stylus is a tool because our main SDK is in C. Because our main SDK is in Rust. The tool that we use to interact with Stylus is called Cargo Stylus. Cargo is a tool that comes with Rust, but you don't have to. But you can work with it with other languages. So we have Cargo Stylus deploy. We give it the WASM file and of course the endpoint and the private key, and it will do both stages. We said that you need to deploy and then activate. Cargo Stylus deploy by default will deploy and activate, and it will tell you which key it deployed to. And then now that we know what's the key, I can start issuing transactions to. And this I'm going to do with Cast. So Cast, if you don't know it, then you probably should. Cast is not a tool designed for Stylus. It's not a tool that's aware of Stylus as a thing. It's a tool designed to work with EVM chains. And it's a tool that you can give it functions. It's a very nice CLI utility that you can tell it, basically, I want to call a contract. This is the address of the contract. This is the endpoint of the RPC, and this is the name and the type of the function I want to call. So call symbol, which returns string, and it will return just like you can believe me, I guess, that the contract returns C token as its token. So interacting with Stylus is very much like interacting with Stylus is very much like interacting with any normal EVM. And as we said, it can go a step further, right? This smart contract can itself call other that smart contract itself can call other smart contracts, just like it was an EVM smart contract. And that's the basic. Sort of like the factorial example. This is a nice example as it shows some things, as the factorial recursion example. It's a nice example as it shows some things, but you shouldn't do it like that. You shouldn't do it like that for a few reasons. First of all, again, the C SDK is very, very bare metal and is very not like you can do it. I enjoyed it, right? It's lots of fun, but like it's a great learning experience. But it has this very, very bare bones approach, and more than that, if all you're doing is a very simple ERC20 that has its own token, but like it doesn't have any important math going on or anything weird computationally wise, you probably shouldn't use the stylus because when you things like load and store, we can't. If you do it in stylus, if you do it from WASM and if you do it from EVM, interaction with the storage is almost the same. We do in stylus have some caching and some stuff, but like if you read and write once, it's the same amount of interaction that you will have with the storage as normal EVM. So we didn't really cut costs and we didn't really charge you less for that interaction. The next example I'm going to show you is an example that I love. It's an example that I didn't create. Wait. Okay. It's not an example I created. It's an example that was created by Chris Cordell, who is an integration engineer. And I think it's a great example of things that stylus can do. And I will share screen window there. Yes, sure. Yeah. And he created this example. You will notice I stole two of his slides for my presentation as well. And it is a great example for two reasons. First of all, it shows using the SDK, which is how you can interact with, how you can write Rust smart contract, Rust smart contract without having to think about all those little corners, and because it shows something you specifically can do with stylus and specifically cannot do with EVM, because it is more computationally heavy than EVM can really handle. So we've gone over those. Chris Cordell is an integration engineer, so he has lots of links to if you want to get started with Rust on stylus. We have many interesting resources. Testing, as you will see, as you might have seen, deploying locally. You can run locally Docker node that you can work with. There are testnets, Arbitrum one. This is actually, I think, a little old because right now you can test just on Arbitrum supported because stylus exists on Arbitrum supported, on Arbitrum 1, on Arbitrum Nova, and on many other Orbit chains. You can use stylus smart contracts. So Rust SDK is designed to be almost the complete opposite of what I've showed you, right? I've showed you if you want to really write down and handle all the bits and bytes, Rust SDK is designed to do as much as possible of that for you. You can be very, it is very solidity oriented in the like it's designed to make you feel at home if you know your solidity and how storage and things work in solidity. And this is an example. This is like if you create a new project, this, I think the counter, this is what will be created. So you create, if you use the Solidity, the Rust SDK, you create a struct that will be the entry point. That will be like the main struct, and its functions will become the functions of your smart contract. So this one created a counter struct that has a simple count, and because Rust supports those things, it has a storage U256. So its type is a U256, and you don't have to do weird things with pointers and stuff like I did in the C. So counter, this is a counter implementation that is very straightforward, right? You can get the counter, which will read from the counter. You can set the counter to a thing, and you can increment the counter. So you see here, all the code is very it's quite simple Rust. It's quite straightforward Rust, and it is translated very directly to to what the transaction will do. You don't have to think about selectors and stuff. And you see each one of those returns a result, and the result will either be like what your function returns, or the vacuate is the error it returns if you return an error. And then Chris, thinking like, let's do something interesting with Stylus. What can we do with Stylus? What can we do that's fun and interesting and compute heavy? And one great answer is chess, right? A chess smart contract. I want to implement a chess smart contract. I want to make full chess. So like an 8x8 board with all the game pieces, all the moves are possible. There are many options, many legal moves in chess. Many legal moves. You need to make sure if every move is legal. You also need to look at things like tie resolution, right? Like if the same thing happened, and Pat, I'm sorry, I'm not great in chess, but like there are like some weird scenarios that you must be able to take into account, and of course, make sure that just making sure that the move is legal is itself not trivial. I didn't check. Chris said that when he checked, he saw like an EVM implementation that was 6x6 chess and used like I don't remember, like millions of gas for a single move or something like that. But this is a full 8x8 chess. So general approach is like, well, to present a chess, you can use it as a bitboard, and you present different pieces as where they are on the board, and you can and there are interesting things you can do with XOR and things like that. But instead of going too deep into all options, you can find an existing library. Somebody must have already done it in Rust. When you choose a library for Stylus, there are a few requirements you need to keep in mind. First of all, Stylus, you need the smart contract must be small. And it must be no STD. No STD means you can compile it without the standard library. So no malloc, no, I think there is alloc, but no IO stream, no, all of those things don't exist on chain. And if you just let the contract have them, it will be too large. It cannot have parallelization because we don't have parallelization on chain. No async features, no randomization. Nothing on chain everything on chain is deterministic. And it says currently not float by coming soon. I'll put a little star on the coming soon part, but maybe like we can do it, but currently no float. So if you try to send a smart contract with a floating point instruction, Stylus the chain will just reject it. So yes, such a Rust library exists, and it's called Chess Engine, and this is what Chris used. Now let's switch to screen and share screen and window share. Nice. Okay. So stylus chess source. Okay. So as we see, the main thing, the basic is stylus chess, which is in many ways the smart contract with all its storage and everything. And the functions you define for stylus chess will be the functions that the smart contract has. So it has how many total games were played, and get turned, and then it has play move, right? So play move gets as input from which row, column, to which row and column, and which game number, because you can have multiple games here. And the board itself gets board from game number. Yeah. Wait, so play move. Okay. So what it will, and now I'm writing pretty standard Rust code, right? So I am part of the interesting thing that he did was to be able to store a full state of chess in a single U256. If you think about it, like every piece needs to have like a location. It just fits in a 256. You can store the full state of the board, going piece by piece. And so to play a move, you see who is the current player. The current player is the one sending the transaction, right? And you know if they are player in this game, and if they are black or white, and if it really is their turn. So you check that the message sender is really the current player, and then you just all those are functions of the internal of the chess library that he used. So you just need to do a simple boilerplate that goes from the chess library to smart contract, and from the smart contract to the chess library, and with less than 400 lines of code, you get on-chain chess. And this is a cool example. I will show you this example, and then we show the part, I think. Okay. So again, we're talking Rust, and we are talking Rust. So what we do, you will forgive me if I open a text file with all the commands I'm going to do. You can see the private key. It's okay. Those are already here. So what I do is I issue cargo deploy. Let's do it. Cargo stylus deploy. Unlike what I did first, I'm not going to point at a WASM file, because this is in a Rust environment, so it knows to find the right file. And I do need the private key, and I'm not going to give it no verify. One thing that we had to solve when we did stylus was you want to verify a contract. Even for Solidity. For Solidity, a large part of it is that it's actually verifiable. So you can, if you go to Etherscan, you can see not just the EVM smart code, which is the only thing that's deployed on chain. You can see the Solidity smart code. But how does ethers can know that it's really the solidity smart code you are reading, right? Because it's very easy for me to write a malicious contract, deploy it, and not have the malicious part in the solidity that I show you. It's very hard to make that connection. So solidity is verifiable. So you can make sure that if you compile the same code twice, you will get the exact same result. Rust is less meant to be verifiable, so we had to do some work around it. You saw here using Docker, it has to be x86. It's weird things are, some weird considerations have to take place, but we did make sure to give specifically Rust that verifiable option, that you can make sure that you can write a smart contract in a way that will make sure that compiling it twice will compile to the same binary, and that's why you can upload your Rust code and prove that it really is the Rust code of the smart contract you deployed. So people only have to review your Rust code and to make sure that you are not malicious. So the first thing we do is stylus deploy. We deployed it and to here. So we will just this, and we need both black and white, right? Because it's chess. So the first thing we call is create or join, which will create a new chess game. The second thing we call will be create or join from the black player, right? So it's using the private key black, and it will join that game. And then we're doing something that doesn't really work on chain. So if we actually develop this into like a stylus, into a large UI, you can have UI that just reads the game, that just reads the game board and displays it in UI. But here, because I am running on a local dev machine, we took a shortcut. And we took a shortcut where stylus smart contracts in debug mode only, in debug chains only, and this is a local debug chain, can print things to the node output. And so we created this function. It's not very useful for an on-chain active smart contract, but it is very useful for something that you are running on your local node. And that will, you see, stylus says that's because we are running a smart contract, and this smart contract wants to print those. Did I do chess address incorrectly or something? Yes, I did. Chess address. Okay, that was an old deploy. I don't want to. Let's do this and private key. Private key black, creator join, and voila. I firstly just used the smart contract that I deployed earlier when I prepared this talk. So this is the smart contract that we deployed now, and this is the state of its game. And then I can make a move. Just you can see here the white pieces, the black pieces. The red and green pieces are places that are under attack. Like the green are things that the whites are attacking, and the reds are things that the black player is can capture in the next move, and then we do again cast send. So cast, as we said, it's a normal. It's not designed for stylus or anything. It's not a tool that we wrote. It's the normal cast, and we just training at the node, and we ask it to play a move, and we give cast needs cast needs to know exactly the function declaration because it needs to compute the selector, and then we give it the input. So we tell it basically to move soldier, and then we can call print game stat and see that the soldier has indeed moved, and that these two are now painted greenish because they are under attack. What more? Oh, I wanted to show, maybe it's here, gas used. This is how much gas it costs. It's not going to cost this much gas in Arbitrum 1 or Nitro because you also spend gas for every transaction for posting it to the layer 1. But this is how much gas the L2 needed, right? So just think about how much gas something like that would cost on EVM if it was even possible, and compare it with what we do here. That was me, and that's what I had to say. And we're almost exactly in 2 hours.
Awesome. Thank you so much, Tsahee. I'm just curious how much it would cost on Ethereum.
So I think that a full 8x8 board will not be possible. Like not in a block. My guess is it doesn't fit in a single block.
Okay, awesome. So we've got to our closing questions, let's say. We would like to ask you some questions from the community, some of them about your journey in Web3 and how you started. So maybe we'll start with just what made you, like, what did you do before joining Web3 or before discovering blockchain in general?
So I used to be, I worked in Annapurna Labs, which was then sold to AWS. I was always an embedded engineer. I was always a low-level guy. I was part of the Graviton processor. It was a team that, like, the first Graviton 2 that launched Linux did it right next to me on my table. And then at some point, some friend posted a Facebook message about, and what I like to say is I didn't know anything about crypto except that I don't like Bitcoin. And then some friend posted on Facebook a message about Ethereum is going to move from proof of work to proof of stake. And I thought, Ethereum is a name I kind of recognize, and like it's going to be more environmental, and that's like the thing I didn't like about Bitcoin. That sounds interesting. And 6 months later, I was, all in podcasts and like reading code through the night and like reading smart contracts and trying to understand everything. And I remember a night specifically where like waiting for everyone to fall asleep so I can go and read code. And I was like, I need to go work in crypto. And that's like, and that's where I joined Offchain Labs about 4 years ago. I joined Offchain Labs just as they launched mainnet Arbitrum 1.
That's awesome. I think it's a good advice for our developers here as well, as many of them are just like joining now or getting to know the ecosystem better. So you already started explaining about it, but how did you start in the ecosystem? What did you do in Offchain Labs? If you want to expand a little bit on that.
So when I joined Offchain Labs, I had one thing that I was a little worried about, and this is, as I said, I knew that I was joining just as they are launching just as they removed so they had like a beta, a whitelisted Arbitrum 1
live on Ethereum. And just as they removed their whitelist, like actually opening it up to the entire public, this is when I joined. And I knew that they're going to do this. And I was a little worried. I was like, so what will I have to do? Like, what will it all be maintenance work? And about 3 weeks after I joined, we had an amazing engineer called Lee that did like a small experiment on the weekend, and the result of the experiment was successful. And a few weeks after I joined, I remember a meeting with Lee and Harry, the CTO and one of the co-creators, and we're like, okay, we're going to build everything from scratch better, and this will be called Nitro. And that's how I got to be on Nitro on the very, very first days. Yeah, and now I've been there for 4 years, so I'm the one that knows how this system was built from the bottom up. I wrote some of the I even wrote the one-step proof smart contracts, and but mostly Rust and Go, like the code down there.
Okay, that's awesome. So it takes me to the next question, but what is your, let's say, what's your favorite thing in what you do, or in what you're doing right now, at least?
My favorite thing is I'm working with very smart people. I'm working with people that. Okay, so I've worked with smart people in the past, right? There are smart people in AWS. There are smart people everywhere. Smart people tend to be people that are hard to work with. And currently, I work with people who are very smart and very easy to work with, and are very much about fundamentals. And like, I think that crypto has a few different companies. Some care very much about the fundamentals, and some care very, very little. And I'm happy to be in a company that does care about those, about building things right, about having things proven from day one, and putting emphasis on building stuff and not on hype. And and I love being with a bunch of people that are very smart, that are all working on work with research people, and they're all working on things that are happening right now, right on the edge of technology, and you're sitting and having conversations with them. And I was often awestruck by how smart are the people I'm working with, and how easy it is to work with them. I will talk to them, and they will say something like, yeah, but, and they will say something very smart, and I'll say, yeah, but, and I will have a small addition, and they will pick it up immediately and just run with it if it's good. Not always. Not always my ideas are good, but when they are, they get treated as such, and I love it.
Awesome. So do you have any tips that you think this is the right place to share with developers, or say more specifically Web3 developers who are starting or trying to get to the next stage?
I think, I don't know, look at fundamentals, really. It's find the people that believe in the technology, because you need to be you will have people doing unreasonable things. There is a lot of, in this industry, you will find many people and many bodies that are willing to do things that they shouldn't. And I'm not talking like breaking the law. I'm talking making shortcuts that we're sitting on billions of dollars. We need to have a sense of responsibility. And find the places that really care about decentralization. Find the places that really care about making things done right and securely. And it doesn't mean that everyone must agree with them, but that they believe in what they do. and 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 attach yourself to those people.
That's awesome. By the way, there is a question from the audience. Um, let's bring him up to the stage as well. Hey, Ariel. I think you can open your mic. Feel free to.
Sorry. Okay, so first of all, it was a great presentation. And I wanted to ask you, I'm a new developer, and I want to, and as we look at the ecosystem of blockchain, we have so many paths to take. So what is your advice about what to learn, if it's Solidity or Rust or whatever other language or something like that?
So I think that if you want to write smart contracts, Solidity is the leader. Like, even if you want to use Stylus, you should know Solidity. I just to interact with other smart contracts, just to understand just to understand the environment. And there is so much to read. There are so many fascinating smart contracts to read. Like the I forgot the name. I'm blanking out. But there are AMMs. Just understanding how things work is very, very interesting. I think find the thing. It's a cliche, right? Find the thing that you like, and then find someone that will pay you to do it. I don't know enough about the industry to tell you what will, where there is money and where there is more work. But I keep always believing that really knowing how things work deep down, right? Like be the Solidity developer that knows what are function selectors and how they work and what it means and how you can save a few gas by using this instead of that, and be the Solidity developer that's better than an LLM, basically.
Thank you very much.
Awesome. Thank you, Ariel. I wanted to ask one last question, which is mostly what would you recommend avoiding and mistakes that that you know are common in the field, or yeah.
I will sound like a broken record. Avoid hype. Like,
Avoid hype.
yeah, there is. I mean, as a developer, okay, as a businessman, hype all the way. I'm not in a place to give financial advice. As a developer, find ask why. Ask why is it better? Like, so many, I see so many projects that collapse under a simple why, or why is it better, or like when people say we prove this, do they prove this? Like, is it actually working? Is the technology that they are referring to actually exist, or is it some daydream about something that they think, or sometimes people will make claims about things that they are actually developing. That's good. There are many people that are actually developing useful things that are not ready yet and are already talking about them. That's okay. But like, yeah, don't go for like the places that do, I don't know, LLM, AI, NFTs, that like it's very easy to throw in a bunch of buzzwords and make something sound almost and maybe get some money, but it's very easy for those places to be closed.
Awesome. Thank you so much. That's some great advice. So I think that's it. That's most of my questions that I've prepared, at least. If anyone from the audience wants to still ask one or two last questions, as long as we still have some of Tsahee's time, this is the time. If not, Tsahee, if you have anything else you would like to add or finish with.
we're hiring. As I said, there are many places available. Like just check Offchain Labs or Arbitrum, and you will see. Good luck. Have fun, and I don't know.
Awesome.
And thank you for having me.
So thank you so much, Tsahee, and thank you to all the participants who has joined us today. Please help us grow and follow us on X and other social media. We will really appreciate it. And see you at the next meetup on September 3rd. We're gonna host Kugan Brennan, the Tech and Education and Developer Relations at Polygon. So all the details will be available through our website on web3devs.org. And also on our Luma and Meetup pages. If you want to take active part in the community or speak in one of our next events, please let us know and reach out through our Telegram or website. And for those listening to us on the first time, we are the Web3 Developers Underground. We're all about technical content, open source, no shilling, and all done by devs, by builders, for builders. And thank you again, Tsahee. It was awesome. Thank you so much.
Bye-bye.
See you next time.
See you.